Look, I know exactly how you're feeling right now. There is this massive cloud of exam anxiety just hovering over the metals and nonmetals chapter, isn't there? It's a heavyweight topic, it's super dense, and honestly, it feels like there's just an endless, impossible list of properties you have to memorize. But hey, take a deep breath. Seriously, because this explainer, it's your absolute secret weapon. We're going to take this massive, intimidating chapter and distill it down to a one-shot revision that targets exactly what you actually need to know to score big. So let me ask you, are you ready for the board exams? And if you're hesitating right now or thinking, absolutely not, do not worry. Our whole goal today is to strip away all that textbook fluff. We are absolutely not going to sit here and read out endless, boring paragraphs to you. Instead, we're focusing entirely on the highest yield questions, the tricky little exceptions, and those specific, sneaky traps the examiner's just waiting to set for you.
Okay, here is our playbook for today. 1. We'll master the key exceptions. 2. The reactivity series mnemonic. 3. Acid reactions and their exceptions. 4. The properties of ionic compounds. And finally, 5. Metallurgy, specifically roasting versus calcination. Let's just jump right in.
First up, Section 1, Master the Key Exceptions, the Rule Breakers. You know, when it comes to physical properties, examiners really don't care about the basic rules. They want the anomalies. Every single point we're covering right now is a highly expected multiple choice question. Normally, nonmetals are gases or solids, right? But bromine? It's the only liquid nonmetal. Metals are solid, obviously, except wait, mercury is the only liquid metal. Nonmetals shouldn't conduct electricity, but graphite absolutely does. They shouldn't be shiny, but iodine is beautifully lustrous. And they definitely shouldn't be super hard with high melting points, yet diamond completely breaks all those rules. You've got to lock these into your memory, guys. And speaking of rule breakers, let's look at the metal side. Metals are supposed to be rock hard with incredibly high melting points, right? But then you have sodium and potassium. They are so soft you can literally cut them with a regular kitchen knife, no joke. And then gallium and cesium. They have such incredibly low melting points that if you simply placed a piece in the warm palm of your hand, it would literally melt into a puddle. Take a mental screenshot of these anomalies right now because they will show up. Moving on to Section 2, the reactivity series mnemonic, decoding chemical clashes. To predict chemical reactions and effortlessly solve those tricky displacement questions, you absolutely have to memorize the reactivity series. And we have a literal cheat code for this. Katrina ne car mangi alto zen Ferrari per bihe q milli silver Audi. I love this. This mnemonic brilliantly orders the elements all the way from the highly reactive potassium at the very top, down through sodium, calcium, magnesium, aluminum, zinc, iron, lead, hydrogen, copper, mercury, silver, and finally right at the bottom, the completely non-reactive gold. If you can just remember this one silly sentence, you'll literally never fail a displacement question again. So using that very series, let's look right at the top, potassium and sodium. Because they are the ultimate heavy hitters of reactivity, examiners absolutely love to trap you with this classic question. Why are they stored in kerosene? When this comes up on your test, please don't write a giant paragraph. Just deliver the exact, concise answer the examiner wants to see. They are stored in kerosene to prevent accidental fires. It's really that simple. These alkali metals are so explosive, so ridiculously reactive, that if you just left them sitting out in the open, they would vigorously react with the oxygen or moisture in the air and literally just catch fire. Now, while we're on the topic of oxygen reactions, you absolutely must know this definition. Normally, metal oxides are basic, plain and simple. But amphoteric oxides, they are the two-faced tricksters of chemistry. They can act as both acids and bases. Aluminum oxide and zinc oxide are your key examples here. Aluminum oxide's ability to react with both hydrochloric acid and sodium hydroxide to form salt and water is an absolute guaranteed test favorite, for sure. All right, Section 3, acid reactions and exceptions, water and acid clashes. Let's look really closely at how these elements misbehave when they meet water and acids. The trick here is understanding the varying, kind of diva-like demands of the metals. Sodium and potassium are so eager, they react violently even with cold water. Boom. Calcium reacts with cold water too, but it floats. Magnesium is a bit pickier, you know? It demands hot water, and it also floats. Now, why do they float? Well, that is a highly expected question. It's because hydrogen gas bubbles form and stick to their surface, acting like these tiny little life jackets, just pulling them up to the top. Finally, a bit lower down the series, aluminum, zinc, and iron only react with steam, And this is absolutely crucial. They form oxides, not hydroxides. Do not mix that up. Now let's talk about acids. Usually, when a metal reacts with an acid, hydrogen gas is released. Pretty standard. But nitric acid is basically the thug of the chemistry lab. It's a remarkably strong oxidizing agent. So instead of letting that hydrogen gas just peacefully escape, it forcefully oxidizes it into water. But hey, every thug meets its match, right? The two bosses that completely break this rule are magnesium and manganese. When they meet nitric acid, they basically say no way and force it to release hydrogen gas anyway. Remember these two rule breakers. And speaking of aggressive acids, we really have to talk about aqua regia. Remember the bottom of our reactivity series mnemonic? Gold and platinum? They don't react with practically anything. But if you actually need to melt them down, you bring in aqua regia. It is a highly corrosive, intensely fuming liquid, capable of dissolving even the most stubbornly unreactive noble metals. It's powerful stuff. But here is the really crucial point. How do you make it? Aqua regia is a mixture of hydrochloric acid and nitric acid. But the ratio? That is highly tested. You must memorize this exact number. 3:1. That's 3 parts hydrochloric acid to 1 part nitric acid. Please, whatever you do, don't mix that ratio up on exam day. Okay, section 4, properties of ionic compounds, the salt analogy. The absolute best way to score full marks on ionic bonds is to just use a really simple mental model. Whenever you get a question on this, I want you to just picture common table salt, sodium chloride. If you picture salt, the properties become incredibly obvious. Is salt hard? Yeah. Does it melt easily sitting in your kitchen? No, it has very high melting and boiling points. Does it dissolve in water? Yes, but it definitely won't dissolve in organic solvents like kerosene. And finally, the single most tested property, conductivity. Solid salt does not conduct electricity because those ions are firmly locked in place. It only conducts electricity when it's melted into a molten state or dissolved in water, because only then can the ions actually move around freely. And if the examiner asks you why regarding literally any of those physical properties, like why is it hard, why is the melting point so high, this single golden phrase is your ultimate cheat code. Just write down, because of the strong electrostatic force of attraction between oppositely charged ions. It takes a massive, massive amount of energy to break that strong bond. Memorize this exact phrasing, word for word. It's money in the bank. Finally, we've made it to section 5, metallurgy, roasting versus calcination, extracting the heavyweights. Listen up, because this is often the highest weighted topic of your entire exam. How do we actually go about ripping these metals out of the Earth's crust? Let's start with the low reactivity metals that are found as sulfide ores, like mercury's ore, cinnabar, or copper glance. The extraction here is actually a really straightforward 2-step process. Step 1, you heavily heat the sulfide ore in the presence of oxygen. This forms a metal oxide. Then, step 2, you heat that oxide even further to rip the pure metal right out, which, by the way, releases sulfur dioxide gas in the process. See? Totally simple and manageable. But what about the mid-reactive metals, like zinc? Now this is where you get the ultimate comparison question on your board exam. Roasting versus calcination. Here's the deal. If you have a sulfide ore, you use roasting. This means heating it with oxygen, and it produces harmful sulfur dioxide gas. But if you have a carbonate ore, you use calcination. This means heating it with no oxygen used at all, and it produces carbon dioxide gas. Ultimately, though, both of these methods result in a metal oxide. So once we finally have that metal oxide from either roasting or calcination, we have one final step to do. We need to get rid of that oxygen. So we invite carbon to the party. Carbon acts as a highly, highly effective reducing agent. It essentially just swoops in and steals the oxygen right away from the zinc oxide, turning itself into carbon monoxide and leaving us with beautiful, pure zinc metal. We've covered the exceptions, the properties, and the extractions. But examiners really love to test your logic with these tricky case-based questions. Think about this. If you have 4 unknown metals, and metal D can't displace anything, while metal B displaces absolutely everything it touches, how do you rank them? Take a moment to think about that. By combining your new understanding of displacement with that mnemonic cheat code we learned earlier, you literally have everything you need to deduce the exact order. Now that you have the complete playbook, which previous year's exam question are you going to go conquer first?
So much for watching. I'll see you in the next one.